we're under standard conditions for something like this, calcium carbonate, solid, we want to go to calcium oxide plus CO2 gas. Well, we could figure out what delta G naught is at 290 Kelvin. There are two ways that we could do this right now. It turns out there's going to be more ways we can do it. As we go on. Let's take a look at the data. And so we need the delta G of formation. It's probably the easiest way of doing it, or the delta H's and the delta S's. In this case, I'm going to calculate the delta H's and delta S's because we're going to change the temperature. And if I use the delta G's of formation, the temperature is only good for 290 Kelvin. And so let's take a look at the data for all right, so again, we're going to use delta H naught at 290 Kelvin plus T, which is going to be 290 Kelvin. There's delta S naught at 290 Kelvin for this. Although it would be easier to calculate it from delta G's of formation, the products minus the delta G's of formation of the reactants. We are going to need the delta H and delta S data. All right. So we're going to go to calcium oxide here and figure out the delta H of formation of calcium oxide, minus 635.1. We have 1 mole of that, so it's minus 635.1 kilojoules. 1 mole of CO2, which would be carbon dioxide. Minus 393.5. So we sum up the products, 1 mole, and then minus the reactants, calcium carbonate, minus 1207. We have 1 mole of that as well, so minus 1207 kilojoules. Okay, so let's go ahead and calculate what our delta H value is for this reaction. Get 635.1, 393.5, 12, 7, 178.4. So this comes out to plus 178.4 kilojoules, which tells us it's pretty, pretty spontaneous, non-spontaneous, or mildly non-spontaneous? Yeah, this is pretty non-spontaneous, plus 178.4 kilojoules. And so we got that going against this reaction. Let's take a look at our delta S. Our delta S should be good because we're forming the gas here. And so we'll just look at the entropies of the products, the entropies of the reactants. So calcium oxide, the entropy is the third column, 39.75. 39.75 joules per mole Kelvin, got 1 mole, plus CO2, which is going to be 213.7. Again, 1 mole joules per Kelvin, minus calcium carbonate, which will be 92.9. 92.9 is fairly high entropy. You got the carbonates. So let's take a look at this. 39.75 plus 213.7 minus 92.9, 160.55. Actually, I'm not allowed this digit. Sometimes when I'm not allowed this digit, because it's like I got the 10th, 10th, and single digit, I'll subscript it to indicate. Just to keep track of sig figs. And so here I'm allowed 1 decimal place, so this is okay, 0.5. And then I'll subscript an extra. I usually carry 1 extra joules per Kelvin. The reason I carry 1 extra is to avoid round-off error. Well, the entropy is favorable, and so we just have to overcome this enthalpy, and we can do that by bumping up the temperature here. And so basically, what we need to do is we need to cancel out this term here. This term is going to be 178.4 kilojoules. We're going to cancel out this term by altering the temperature, and this is going to be 0.1605, so 5 kilojoules per Kelvin. Get the units the same. And so we just increase the temperature until we get an entropy that works. I did a mistake in my equation. Otherwise it doesn't work. Minus, it's going to be minus the delta. Sorry. And so what temperature will that force us to equal 0? That's what we're trying to do. So we're going to try to bump up this term. And so we just solve for the temperature. And solve for the temperature here. The temperature is just subtract that from both sides. And then divide it by this. Or either that or add it to both sides. And so basically it's going to be 178.4. 178.4 divided by 0.1605 gives me 11. We have 11. All right, looks like I'm allowed, this is multiplication. We should have 3 or 4 sig figs here. Decimal place, so I should be allowed this. 11.1 Kelvin. All right, that's in Kelvin. What would that be in Celsius? So let's do that. This would be 838.1 Celsius. And so if we heat this to 838, 840 degrees C, then we should be able to do this spontaneously.
I have a question. So under what conditions do we have delta G equals to 0? Because for a reaction it isn't really 0. I didn't understand that on the
Okay. Right now, at 298, oops, this is not at 298 Kelvin. This is just delta G, sorry. At 298 Kelvin, what is my delta G? Okay. At 298 Kelvin, my delta G is going to be this. Rather than plugging in, this, leaving that as a variable, I'll plug in 298 Kelvin here. And so if I do that, I'm going to get 298. Actually, since I go for more sig figs, I'll go 298.15 times this, 0.16055 equals 47.86. And so at 298 Kelvin, I have 178.4 kilojoules minus 298.15 Kelvin times 0.16055 kilojoules per Kelvin. And this gives me 178.4 kilojoules minus 47.8, 867 kilojoules.
That's 130.5.
And it comes out to 130?
130.56.
Okay, 130.56 kilojoules. 130.56, is that highly non-spontaneous? Highly non-spontaneous. But 298 Kelvin, this is highly non-spontaneous. Why is it highly non-spontaneous? Even though the entropy is good. Even though the entropy term is favorable, it's not big enough. You know, the entropy term is only multiplied by this factor of 298. And so that only gives us minus 47.8. We need minus 178.4 to cancel it out. And so one thing we could do is we could try to alter the temperature. I skipped some steps here. Maybe I shouldn't have skipped some steps. Probably shouldn't have skipped some steps. Because we did an example of this previous calculation. And so let me put in those steps I skipped. So it's still highly non-spontaneous at 298 Kelvin. And so we could just say, okay, we're stuck. It's not going to happen. If you have calcium carbonate, it's not going to happen. But you know, I watched a TV show on the Discovery Channel about this reaction. This reaction was critical reaction. It was a whole bunch of stuff. One, you know, in this TV show, they're talking about the fertile fields of Italy or someplace, and how they could produce lots of food. Since they could produce lots of food, they could do chemical reactions. One of the chemical reactions that they experimented with was this. They were able to heat up calcium carbonate to very high temperatures. Since they were able to heat up calcium carbonate to very high temperatures, they were able to form calcium oxide. Since they were able to form calcium oxide, they were able to make concrete. And so they're talking about Romans.
CO2. Is that CO2 or H2?
Oops, CO2, sorry. So, this is a very important reaction because this is normally non-spontaneous. So if you look at the rocks around Rome, you know, carbonate consisting of the carbonates, calcium carbonate, limestone. And what they did was they were able to heat this up to very high temperature. And when you heat it up to a very high temperature, then it goes a chemical change to form the calcium oxide. Calcium oxide is lime. You know, lime is a key ingredient in concrete, and so they were able to make a whole bunch of concrete structures in Rome. And so, so normally this is non-spontaneous. If you have limestone, it doesn't decompose. And so what we just did was, at what temperature will it decompose? How hot did they have to heat it up to? Well, they had to heat it up to a very high temperature. And they were able to do this with the coals. And so what we can do is we can say, okay, it may not be spontaneous, but we already know that if the energy is going up and the entropy is going up, we know that this scenario is a scenario where it becomes more spontaneous at high temperature and non-spontaneous at low temperature. So we just got to figure out what temperature this is. And so what we do is we just calculated delta G naught at temperature T. We know something. We know that the enthalpy, it's reasonable to assume that the enthalpy, you know, at temperature T and the entropy change at temperature T are going to be roughly equal to that at 298 Kelvin. We have to assume that. And so, well, the enthalpy term is plus 178.4 kilojoules. Now, this is going to be minus T, and the entropy term is 0.16055 kilojoules per Kelvin. And so at what Kelvin temperature will this term cancel out that term? If this term cancels out that term, then this plus this term will yield, or this minus this term will yield 0. So I just set it equal to 0 because it's the easiest way to solve it rather than guessing a whole bunch of numbers here, and just solve this algebraically for the temperature. The temperature is just going to equal, we'll add this to both sides, so it's just going to be 178.4 kilojoules divided by kilojoules per Kelvin. This comes out to 11. Actually, I wasn't allowed that many. I'm only allowed 3 figs here. 1111 Kelvin, which is 838 degrees C. I'm going to plug that in here. I'll get plus 178.4 minus 178.4, so I cancel out that term there. And so that's what I'm doing here. We're just adjusting the temperature to either increase this second term or decrease it to change delta G. All right, so we could use temperature, and in this case we could use temperature effectively. Sometimes we can't use temperature, so for example, if the temperature is too high, let's say the temperature is 20,000 Kelvin. If the temperature is 20,000 Kelvin, are the Romans going to be able to build a fire that's going to get 20,000 Kelvins hot? Are you going to be able to build a fire that gets 20,000 Kelvin hot? No. And so if the temperature is like some ridiculous temperature, like 20,000 Kelvin, well, I guess you could shoot it off into the sun or something like that, have the reaction go that way maybe, but it would be very difficult to do here. I mean, not impossible maybe, but whatever. Maybe challenging. Likewise, if the opposite scenario, if we had the opposite scenario where the energy went down but the entropy also went down, then that's spontaneous at low temperature. Well, sometimes you do the calculation for low temperature and you get, oh, it should go spontaneous at minus 120 Kelvin. Is that an achievable temperature? Minus 120 Kelvin? You say, oh, the math is right. I did the calculation correctly. But is minus 120 Kelvin possible? It's impossible. It's not feasible to get that temperature. And so even though, high temperature should go spontaneous, at low temperature some reactions should go spontaneous, sometimes those temperatures aren't achievable, and you should recognize that those temperatures would be very difficult to get. Well, sometimes we don't want to heat it so high, so we try different things to help us, for example, we could try coupled reactions. We could, couple this with something else. But this one would be kind of hard to do a coupled reaction because this is our desired product, calcium oxide, and we don't want to change that. We need that. This is a byproduct, CO2. They aren't going to use it for anything construction-wise, right? And so here we could do that, but what reacts with CO2 that you could couple this reaction with? Because if we can get a favorable reaction with CO2 and something else, then that could help us. And so you have to think, what reacts with CO2? Can you think of anything? Yeah, there are things that react. I wasn't supposed to erase that one, but there are things that can react with CO2. That might help us because that might mean that we don't have to heat it as hot. I mean, 840 degrees C is pretty hot temperature. It's extremely high temperature. And so this is why they built special kilns in ancient Rome to heat this thing up. And so if we can figure out something that reacts with CO2 favorably, then we can do that. And it turns out CO2 is a base. Or is it a base? No, it's an acid. CO2 is an acid, right? And so if we react it with a base, maybe that can happen. And so we can react it with a base like sodium hydroxide. And this is what we call a Lewis acid-base reaction. Sodium hydroxide, if we take two of these, it would form sodium carbonate and H2O. Lewis. Lewis acid base encompasses all acid-base reactions, so you see a lot of variety in those types of reactions. So we draw out the Lewis structure to figure this out. This is favorable. And so if we like did a couple this, this has a negative delta G here. And with that positive delta G, it might not, it might not go to zero. It might not, and in fact it won't. It probably won't go to zero, probably won't, but it would probably mean that the delta G is not so big of a barrier. And if it's not so big, then we don't have to heat it to as high of a temperature. Rather than heating it all the way up to 840, we might only have to heat it to some other more reasonable temperature to achieve. But we could try coupled reactions. And so to try coupled reactions, you have to know some reaction chemistry. You have to know the metathesis, the acid base, and redox. We haven't talked much about Lewis. This is a bit more challenging. All right, what else can we do? What else we can do is we tried the temperature. We can try, we can always try a combination of things because a combination of things can yield good results as well. But what we're going to do is a strategy. The next strategy to try, I don't think I numbered these strategies, is to go non-standard. Non-standard means to either increase or decrease the pressure. So in the original reaction, another way to get that to go is to decrease the pressure of CO2. And there are a variety of means of doing that. This is one, you get rid of the CO2 by reacting it with something like sodium hydroxide or sodium carbonate. This is what they do, on the space station, International Space Station, they have to scrub the air in the space station of CO2, otherwise the CO2 concentration builds up. As the CO2 concentration builds up, it screws up your blood pH. It can be toxic. And so what they do is they filter out the CO2. They don't use sodium hydroxide, they use lithium hydroxide. Lithium hydroxide is a little lighter than sodium hydroxide. It's more expensive. And so we could try increasing or decreasing pressure by different means, either chemically or by using what we call a vacuum. Or we can try to increase or decrease the concentrations. Increasing or decreasing concentrations can help us as well. We try to scrub this with solid here, especially at high temperatures to be solid. Well, anyway, in order to use these non-standard, we have to see how concentrations and how pressures impact delta G. So how do pressures and concentrations impact delta G? And so what we need to do is we need to relate delta G and concentrations and pressures. The way we're going to do that is by using Q and K. Q is called the reaction quotient, K is called the equilibrium constant. And what I want to do here, because this is kind of out of order, I don't really like how they did chapter 13, how they placed it. And so I'm going to jump to chapter 15.1 just for a little bit. And so we're going to go to chapter 15 and then we'll return back to chapter 13. This will go to chapter 15. All right, let's take a look at some reactions here. For example, let's look at this reaction, 15.1. With 15.1, let's calculate our delta G for this. Here. So,
I have 2Cu2 plus. Actually, I'm gonna write it again. Write it in there.
that reaction there. And so I need to go to Appendix D and look at copper 2 and copper 1 and tin 2 and tin 4, etc. And then I can calculate my delta G, but it turns out that the delta G for this, is it favorable or unfavorable? And so one way we could quickly do this is, rather than, because copper 1 is not on our delta G chart, unfortunately. Copper 2 is. Copper 2 is common. Copper 1, so rather than using our delta G chart, is there some other way we could figure out is this reaction favorable or unfavorable? Because if I go to A18 and look for the delta G value for copper 1, delta G formation, copper 1. Is it there? Cobalt? No. This page. I have copper 2. I got my delta G formation here. But unfortunately I don't have any copper 1. So if I don't have any copper 1, am I out of luck? No, I don't know if this reaction is favorable or unfavorable, or if there's a driving force or not. What can we do as an alternative? We might not look at this chart. We could look at some other chart. Which chart would you recommend looking at to see if there's a driving force or not? Or we might be able to figure it out. We wouldn't call it the activity series. We would just call it the redox chart, or the. It actually has a name. Do you know what the official name is? The official name is actually in the heading of that. I don't know if anybody caught the official name. I call it the redox chart, or the strength chart. But if you want to know its official name, you see what its official name is? Actually, the official name of this is standard reduction potentials. Electrode is not as common. When you look at a chart, it would be standard reduction potentials. These are all what we call reduction reactions. They're all oxidizing agents being reduced to reduction. Chlorine has the highest reduction potential. All right, let's see. We would consult this chart and we take a look, because the reaction is this. We have copper 2, so 2 copper 2s plus the tin 2, was it? You have 2 copper 1s plus a tin 4. All these are aqueous. And so what are we comparing here? You recognize it right off? What's the oxidizer? What's the reducer? Copper is the
what about in the reverse direction? Copper is the reducer and tin is the oxide. So we need to compare. We're going to compare these two oxidizers, copper 2 versus tin 4. So let's go ahead and do that. Copper 2 versus tin 4. Find that. And so we start off with chlorine and we go down, down, down. Oh, here it is. This is copper 2, but would we use this equation here? No, because this has iodide. I don't want that. Just keep going down. Good, skip it. Okay. Here's copper 1. Do we have copper 1? No. We don't have copper 1. Here's copper 2. But there's something tricky about this copper 2. You see, this copper 2 goes to copper solid, and it doesn't go to copper 1. And so it's not exactly the same as what we have. And so it's going to behave a little differently because that's copper 2 going to copper 1. And so we might try to do the, instead of doing the oxidizing agents, because we don't have the right half reaction. Actually, we're going to learn, once we get to chapter 19 or so, we'll learn how to figure it out based on this chart. But for right now, let's skip it. Because, if the oxidizing agents don't tell us easily, maybe the reducing agents might. And so let's take a look at the reducing agents here and compare the two reducing agents. We'll compare tin 2 and copper 1. And so what's the strongest reducing agent on the chart? Lithium. And so let's go and start at lithium. Here. This is a very long chart. I'm going to this chart because the chart I gave you in the book isn't there. And so I'll start out with lithium and then work our way back up. Lithium, looking for copper 1 or tin 2. Don't see it yet. Let's go down here. There's tin 2. Actually, there's tin 2 and copper 1. So these are correct because this tin 2 is going to tin 4, and this copper 1 is copper 2. Actually, I had it. Actually, I could have done the oxidizers too. I just missed it. I don't know where I missed it. It's kind of low. Well, anyway, which one's stronger? Tin? Okay. And so stronger to weaker. If one stronger than the others. It turns out this is favorable. Reaction occurs. Well, the problem is I'm missing the appendix D data, so I can't calculate it. And as we go on, we'll see I actually can calculate it. I just have to use an alternate method because I can't calculate it using the equations I gave you so far. But later on, I'm going to give you some more equations, and then we can figure out how to calculate it. But anyway, it's favorable. So if it's favorable, we'd say that there's reaction that takes place, right? There's reaction. Because this tells me that reaction occurs, there's driving force. If there's a driving force, then we say that delta G naught is less than 0. That's it. And so we'd say that this is spontaneous because we're going from stronger to weaker, right? But how spontaneous is it? How spontaneous it is depends on, you know, the gap. You know, if we're going from much stronger to much weaker, you know, that's highly spontaneous, you know, because one side is going to be heavily favored. And so let's say, you know, the products are so reactive, and not the products, the reactants. The reactants are so reactive, right? They're so reactive, they're totally unstable. And the products are totally stable. You know, the products are so stable that it's kind of lopsided, the seesaw, because it wants to form a product. But when you look at this chart, is there a huge difference in the stability between the product and the reactants? Now, when I look at this chart, I say, wow, the products and reactants are, you know, they're right next to each other. It's almost a tie. Can you see it? This is about a tie. You know, what would be lopsided is if we were starting off with fluorine and going to, let's say, lithium ion. You know, that would be totally lopsided because we'd be. And so the closer these things are together, the more even they are in strength, right? And the farther apart they are, the greater the difference in the strength is. And so when I think about this, yes, it's spontaneous, but how big is that driving force? You know, based on the position in this chart, I'd say that driving force is not so big. And I'd guess my delta G value is, you know, what do you guess your delta G value might be in this case? I would guess it's not terribly big, you know, in terms, I wouldn't think it would be a minus 200. A minus 200 would be a very powerful driving force, right? Or minus 100. I'd probably say it's a minus, you know, 5, 10, something like that, you know, because they're so close together. Does that make sense? We're getting a feel for this. But nonetheless, we'd say that, hey, this reaction is spontaneous. So what we want to do is we want to do Chem 1A style stoichiometry with this. And so let's try some stoichiometry. You know, we know that there's a driving force for this reaction. This reaction should occur. And so we're going to do a setup. But now we're going to set it up in a Chem 1B style setup. For Chem 1A stoichiometry, you just do dimensional analysis usually. And you just put it together. Okay, this is what we're going to do in Chem 1A stoichiometry. I'm going to do this chart a little differently than what they have. So for Chem 1B stoichiometry, we start off with the reactants. And so what we're going to do here is we're going to put some amount in here. And we're going to do concentrations of, let's go, I'm going to go 1.00 moles of this, and I'm going to go with 1.00 moles of this. And so I'm going to take these two, and if you look at it, which one would be the limiting reagent, which one would be the excess reagent in this reaction? The tin would be the excess or the limiting? Tin would actually be the excess reagent because if we have 1 mole of tin, we need twice as much copper. And so we would need 2 moles. Do we have 2 moles of copper? We don't. We only have 1 mole of copper, and therefore copper is our limiting reagent. And tin would be our excess reagent here. Well, this is going to go to the 2 copper 1s plus the tin 4 plus. And so let's say we have 0 moles of this, 0 moles of this. And so this is the way we're going to set up the Chem 1B stoichiometry. We start off with the given amounts of reactants. This is a limiting reagent type problem. And then we calculate our stoichiometric change and to figure out what the final or the end result is going to be. And so we consume the limiting reagent completely. So we'd say we're going to lose all the limiting reagent, so we end up with no limiting reagent left over. And then over here, how much of our excess reagent have we consumed? Well, we need half as much tin as copper. So if we need half as much tin as copper, we lose half the amount. And so we end up with half left over. Like that. This is the stoichiometry. Now, how much product do we form? So, if we react how much copper plus would we form? Stoichiometry. 0.5 or 1? Well, atoms are neither created nor destroyed. So if we start off with 1 mole of copper atoms, we got to end up with 1 mole of copper atoms, even though the charge is different. So, and the same thing with the tin. We're going to end up with 0.50. There's an easy way to do this in Chem 1B. In Chem 1B, what we do is we look at the coefficients on here. This is a 2, so we call this minus 2y, or x. I'm calling it y because this is a little bit different than what we're going to be doing. This is going to be minus y, and so that's how much we lose. So y is 0.50, and so that's how much tin, 0.50. I'm going to need double the amount of copper. And then over here, if I lose that, I'm going to gain plus, this is going to be plus 2y. And so it's the same over here. It's going to be 1, double this, and plus y, based on the coefficients, because it's a 2, 1, 2, 1 reaction. And so I could do this quickly in my head in Chem 1B if I know what y is. And I know what y is because I know what the limiting reagent is, so I can figure it out. And so I end up with some excess reagent left over, and then I'm going to end up with 1.00 moles of copper 2 and 0.50 moles of tin 4. And so I just do this. 1 minus 1 equals 0. 1 minus 0.5 equals 0.5. 0 plus 1, because this is the change. So this is plus 1, 0 plus 0.5. And that's where I get those values, because I see how the stoichiometry changes from the initial condition. And it turns out that, is this what I get? No. Do you know what I get in this? If I were to do this reaction, this is not observed. Not observed. In fact, what's observed is this. What's observed is I don't get that at the end. Of this, I'm going to get 0.36 moles. Over here, I'm going to get 0.68 moles. And then I'm going to end up with 0.64 moles and 0.32 moles. And this was not my change here. This is not my change. What was my change here? And so what was it observed? This is what was observed. So if I break this down, what was actually observed is this here. To go from 1 to to go from 1 to 0.36, how much did I lose? I lost 64, so this is, I must have lost 0.64, right? 0.64, that's what we call minus 2y. If that's minus 2y, what was my y? Well, y would be half of that, and half of that would be 0.32. So this must be minus 0.32, which is minus y. And then over here, I gain 2y. Well, 2 times y, well, y is 0.32. 2 times y is plus 0.64, which is 2y plus 2y. That's 2y. And then over here, I get plus y, and we know y is 0.32, so this is just plus y. So in one sense, the Chem 1A stoichiometry works because these coefficients keep things balanced. Right? On the other hand, it didn't work because we predicted there's a driving force, and we predicted this should go spontaneously. But what was the problem here? The problem here was how weak the driving force is. If we have a very weak driving force, where the products and reactants are about equal, then we're going to end up with not complete reaction. First we started with all reactants. We'd like to go to all products, right? But what happened here is the products are fairly stable too, about as stable as the reactants. So we just have a little bit of a bias towards product. And so in Chem 1B, we have to think about, it's not just is there a driving force or is there no driving force. We have to think about the magnitude of the driving force. And then, well, how do we predict it? How do we predict this? Well, this is from experimental observations. And so what we can do is we can do some experiments, some additional experiments to see, if this pattern holds. The pattern is this. The pattern is how much of the limiting reagent, what percentage of the limiting reagent did I lose? So if this are 100, then I lost 64. And so if I lost 64 over 100, what is that percentage that I just lost? 64%. So I might say that the pattern, this is the pattern I'm looking at right now. The pattern of reactivity that I see is that 64% of the limiting reagent reacts. Do you like that pattern? Well, maybe not, but let's see. We're going to do another experiment. In the next experiment, rather than starting off with 1.00 moles, we'll start off with a tenth of that, 0.100 moles. And so we're going to start off with 0.100 moles of copper 2, 0.100 moles of tin 2. This is going to go to copper 1 and tin 4. Those are both 0 initially. And then they do the reaction. You just do this and see what happens experimentally. This is, we aren't hypothesizing. Can you come up with a hypothesis? I hypothesize in that particular reaction, based on the positions in the chart, that we're going to have 64% reaction. Are you going to come up with a hypothesis like that? No. We're going to just take observations and see. Because coming up with a hypothesis would be very difficult for this. But maybe it's good, because how much? So we started out with 0.1. We're going to end up with 0.036. What percentage of the limiting reactant reacted? What is that percentage? It would be, if you made this 100, it would be 36%. Oh no, we have 36% left over. How much did we lose? %. So 64% was lost, 36% remains. And so, is that good? Yeah, it seems like the pattern works, right? The pattern works. So my hypothesis is, in this reaction, we have 64% of the limiting reactant reacts. Okay, so far we have 2 experiments that we observe this pattern. And so let's go to this. We're going to go to experiment 3.
If we go to experiment 3, I'm going to put in 0.100 and 0.100. And so the same thing, 0.100, 0.100. But in this case, I'm going to put in some products here. I'm going to put in 0.100 and 0.100 product. But having products here shouldn't impact it, you know, just should go forward, right? We just have to have some additional product at the end. I still expect the limiting reagent to be the same. You know, the limiting reagent should be copper 2. And I still expect it to have 64% reaction. But in this case, you do the experiment, you mix this up. So we got the same reactants here, but now we just have some product. But when we come to the end, you know, when things stop reacting, we look at the limiting reagent, and what percentage of the limiting reagent did we lose? Well, actually, let's go. If this are 100, if we made this 100, this would be 92. And so that means we have 92% of our reactant remaining unreacted. And that means we lost 7.8% of our,
Where did you get that number? Where did you get it? 0.09?
that comes from experiment. So you would actually mix these together and then see at the end how much remains. What they do, they mix it together, and 92.2% of our limiting reactant remains unreacted. In Chem 1A, our limiting reactant goes to completion and 0% remains, right? That's because in Chem 1A, we restrict the reactions. In Chem 1A, if there's a driving force, it's going to be like this. You're all reactants, and boom, you're all products now. In Chem 1B, unfortunately, that driving force might not be so big in one direction or the other. And so here, only 7.8% of the limiting reactant actually reacted. We can't get any more than this to react. It stops reacting at this point. And so what's your hypothesis now? What's your hypothesis? Do we start our scientific observations with a hypothesis, or do we start our scientific observations with observations and looking for patterns? We don't care. I don't care what the hypothesis is. I'm just looking for patterns right now. You know, and what it means, I don't know what it means. You know, I just thought, originally I just thought that 64% of the limiting reagent should react, but now I have an experiment that says only 7.8%. And so what should I say? I should say that in one reaction 64%, and another reaction 7.8%. Is there a pattern there that you see? Well, let's try another thing here. We know that the reaction is favored in the forward direction because it's got a driving force. Therefore, it should be spontaneous in the forward, and it should be non-spontaneous in the reverse, right? Because it's saying that the products are favored. And so in this, what we call experiment 2, in experiment 2, we'll just put products there. And the driving force is in the forward, so if we put product here, there should be no reaction in the reverse, right? But let's see what happens. If we put product here and just let it sit, after a while, we lose product and we form reactant. And so we just said that the driving force is in the forward, but now there's got to be a driving force in the reverse because we're losing product and forming. And so even though we said, we're going from stronger to weaker, it wasn't so significant. So what happens is we have more of a balance here in the seesaw. And so we have a reverse reaction actually take place. Now, how much reverse reaction do we have? So let's take a look at the limiting reagent on the reverse side. What's the limiting reagent on the reverse side? If we have 0.100 copper 1 and 0.100 tin 4, what is the limiting reagent, the copper or the tin? Yeah, the copper, because if we have 0.100 tin, we need double. And so we need 0.200 copper, we only have 0.100 copper. And so we need double. And so if I were to go backwards in this reaction, then it turns out that the limiting reagent is copper. Now, if I look at the copper and I call this 100, how much of the copper remains unreacted? If this is 100, I just move the decimal 3 over. Move the decimal 3 over here, move the decimal 3 over here, and I get 43% of my copper remains unreacted, which means how much reacted? How much did I lose? What was the change? What's missing here is the change. I don't know why they didn't put the change in. We put the change so it's a little clearer to see. But since they didn't put it in here, we'll have to calculate it in our head. To go from 0.100 to 0.0433, what was the minus? It had to be minus how much? 0.0567. 56.7% reacted in the reverse direction. So 56.7% reacted in the reverse direction. Is there any pattern in the percent reaction of the limiting reagent for this reaction? These are all the same reaction. And they write this double arrow because this double arrow indicates that the reaction can go both ways. Now, is there a pattern in the percentages? No. At least I don't see it because, the percentage is all over the place, right? And so what people do in science is they try to visualize things, graphically. And so maybe it's hard to see the pattern. Is there a pattern in the numbers here? Like 360, 680, 640, 320, 567, 283, 433, 717, and the last, is there a pattern in the end? 92, 922, 961, 1078, 1039. Do you see a pattern in the end ratios or anything like that? And so it might be hard to see. So in science, we try to visualize things graphically. And maybe we'll see a pattern here graphically. And so this is the first experiment. They call it experiment 1, where we start off with 0.100 of the reactants, the blue and the red, and 0 of the products, the black and the green. And so we lose reactants, and we gain products. And so let's look at the pattern. These are color-coded, so we might be able to see a pattern here. I see a pattern: blue, black, red, green. And it's like 2-2. Do you see that? And so maybe that's the pattern there. Okay, in the third experiment, we started with 0.100 of everything. And so the reactants and products. And it turned out the reactants dropped down a little bit, and the products increased a little bit. But look at it here. This was blue, black, red, green. This is green, black, blue, red. Do you see the same kind of pattern here in the product ratios? No. And then this is experiment 2, where we started off with just product here. And look at this. This is green, red, black, blue. When we color code each reagent, it's totally, there's no pattern there. That means, if you were to make a prediction, let me give you some numbers here. I'm going to throw in some numbers here and ask you to make a prediction. How much product I'm going to get and what the percent reaction is going to be. So if I put in 0.389 here, and let's put in 0.176 here, moles, and 0 and 0, can you tell me what percent reaction? How much am I going to lose of my limiting reagent? In Chem 1A, it's easy, because in Chem 1A, we say we lose 100% of the limiting reagent, all the limiting reagents gone. But can you tell me how much? I don't know. I have no idea, because we had 64%, we had 9.8%, we had 56.7% reaction. How much percent reaction do you think this reaction is going to have? No idea. Right? No idea.
And so should we give up on doing Chem 1B style stoichiometry problems because we have no idea where it's going to end up? No, because we shouldn't give up on trying to find a pattern. Yeah, you know, because the patterns are very difficult to find sometimes. The patterns, and you might remember in the quantum chapter when you look at the hydrogen atom spectrum. In the hydrogen atom spectrum, let's take a look at that here. The quantum chapter, which was chapter 8. In the hydrogen atom spectrum, do you see a mathematical pattern here? It turns out there is a mathematical pattern. Do you know the mathematical pattern of that line is that the energies of that line, fit this minus r sub h 1 over n final squared minus 1 over n initial squared, where n final is equal to 2. And so the pattern is minus r sub h, where r sub h is a constant, 1 over 4 minus 1 over n squared, where n is greater than 2. There's an integer greater than 2. That's a mathematical pattern of that line. Was that easy to find? No. And so that's this is the Rydberg equation. So Rydberg found this mathematical pattern. And we call this an empirical equation because did he hypothesize this before? How is this Rydberg equation derived? By observation. This Rydberg equation wasn't derived by all of a sudden he had some hypothesis that, oh, I know, I hypothesized this equation. No, it's just guess and check. You know, you guess to find the pattern. So this is what we're going to do in chapter 15 here. Let me keep guessing. And so, back to chapter 15 here. And so it could be like a mathematical equation. And so this is what you see on the right. You know what they're doing on the right here? They're just guessing. They're guessing that there's some kind of ratio. Actually, this is not the one I actually wanted, but it's all right. You know, so what we could do is we could make some guesses. Guesses might be, there might be a ratio between the products over the reactants. This kind of ratio. And since the copper is multiplied by 2, we can guess a whole bunch of different equations. But I'm going to make a long story short because there are a whole bunch of guesses here in trying to find out a mathematical pattern here. And it turns out there was a mathematical pattern found. Let's take a look at the mathematical pattern. The mathematical pattern is this. If we take not the amounts, because if we use the moles, it doesn't work. If we use moles, the pattern fails. We have to use molarity. And so if we use the molarity, and this is why these are molar rather than, I should have said it's 1 liter rather than moles. If we use molarity, then there's a pattern in the molarities. The pattern in the molarities is this.
if I take the molarity of the copper 1 and square it, I square it because why? Well, copper 1 has a 2 in front of there. And so they tried multiplying it by 2. So if they did 2 times this concentration, and then they tried to leave the tin alone like this, and then they tried adding it, and they tried multiplying it, and they tried a whole bunch of different mathematical patterns. And to save time, we'll just go to the one that worked. The mathematical pattern that worked is this. If we take the copper 1 and square it because of the 2, and multiply by the tin 4, and divide it by the copper 2, which is squared because of the coefficient 2, divided by the tin 2, we get a number. This number is 1.49. Okay. That's at the end. At the beginning, you know, we can do the same. At the beginning here, I mean, we have this, but at the end of this, we'll do the same thing. Look at the pattern. And so we just take the products raised to the respective coefficients, so this will be squared, divided by the reactants raised to the respective coefficients. Look at it, 1.48. And then we go to experiment 3. And do the same thing here. What do we get? 1.48. Do you see a pattern? There is a pattern because it seems to be going to 1.48 roughly each time. And so that's a consistent pattern that we can use to predict the reaction. Now, what this here is, this is what we call K. K is the equilibrium constant. And K is the ratio that it should end up at equilibrium. And it's constant, 1.49, 1.48, 1.48 gives us 1.48.7. That would be our K, our average, based on the experimental data. And so that's our K. That's what it should end up with. When we do the same ratio with our initial, we call that Q. Q is our reaction quotient. And so if we look at our initial, is our initial equal to K? No, it's off. If I did the same ratio with our initials, I get 0. Well, that's too small. It has to be bigger. It has to be 1.49. And so this Q value tells me, well, I'm a little bit too small. I got to make it bigger. That is, I need more product here. And so I'm going to get 4 reactions. If we look at this one, we do the same ratio with our initials, and we get a Q of infinity. Well, that's too big. We have to drop it down to 1.48. The way we drop down this ratio to 1.48 is to make more reactant. And so, and then finally, in this experiment, we get a Q of 1. If we get a Q of 1 here, it's still too small. We need to form a little bit of product to make it bigger. Ratio is either too big or too small. And so this is our initial ratio. Our initial ratio is Q. Our final ratio is K. That's what we're doing here. And so we can do this problem here. I can do this problem now. I can make a prediction because I'm going to say that K is going to be 1.48 sub 7. It's actually sub 6. So I'm not going to round it up. 1.48.6. This is the average K from the experiment. And so now if I want to predict the reaction, I don't use percentage. Was there a pattern in percent reaction? No. What I use is Q and K. I don't always have to calculate Q. For example, if I look at the Q here, the Q is easy. I can just do this one in my head because it's the ratio of the products. So 0 squared times 0 is going to give me 0. 0 divided by that, it gives me 0. So Q is too small. Do you see my Q? This is not the correct ratio. The correct ratio should be 1.486. Now, that means I need to make more product. need to increase, therefore make product lose reactant, and we get forward reaction occur here. If there's forward reaction that's occurring here, I don't know exactly how much. Do I know the percent? No, I don't know the percent, so I'm just going to call it minus X. And I have to do this. Does this work for moles or does it work for molarity? Molarity. So I'm going to dissolve this number of moles in a liter. And so that's going to give me the same number in molarity. And now it's going to be okay. But the problem here is it's not minus X, it's minus 2X, because I need twice as much copper as I do tin. And so this is minus 2X molar, this is minus X molar, this is plus 2X molar, and this is plus X molar. And I have no idea what X is because I don't know what the percentage reaction is going to be. I just know that the final ratio has to be equal to that. And so this is going to give me 0.389 minus 2X molar, 0.176 minus X molar, 2X molar, and X molar here. And this is what we call the equilibrium concentration. So this is going to be the equilibrium concentration, or the end concentration of copper 2 plus. This is going to be the equilibrium concentration of tin 2. This is going to be the equilibrium concentration of copper 1. And tin 4's equilibrium concentration. And so what we do here is this. Let me define Q, the equation for Q. Q is equal to, not the equilibrium concentrations, Q is equal to what concentrations? Initial concentrations. So the definition of Q is this. It's the initial concentration of the products, which would be copper 1, and this has got to be squared, tin 4, initial, divided by the initial concentration of the reactants, which would be copper 2, this has got to be squared, and the tin 2, which is going to be to the first power. Now K is defined differently. K is defined as the equilibrium constant. It would be the exact same ratios. Only difference is we've got to have this ratio at equilibrium at the end of the reaction. All right, and so if that's the case, then this K, this 148.6, has got to be these concentrations here. So I'm just going to rewrite this one more time. It's going to be copper plus squared times the tin 4 plus divided by the copper 2 plus squared and the tin 2. And I'll just put E's for equilibrium, or I should probably call it EQ. EQ, equilibrium. Equilibrium means there's no more change. The things reach the equilibrium value. Well, I have many unknowns here. But, what I do in math, when I have many unknowns, I like many equations and then substitute and solve. And so what I'm going to do is I'm just going to solve it. The copper plus concentration in the equilibrium is also known as 2x. It's going to be squared. The tin concentration in the equilibrium is x. The copper 2 plus concentration is 0.389 minus 2x. This thing has to be squared. And then the tin 2 concentration is going to be 0.176 minus x. That. Do you see what I'm doing here? Substituting. Now, I don't have 4 unknowns. I have just how many unknowns? I only have 1 unknown. And so I just have to solve this for x. Well, how good is your algebra? Well, this is going to be 4x cubed How good's your algebra? Can you solve this for x for me? I'll give you a few minutes to solve this for x. Okay, about how much more time do you need? Does anybody have the answer? Does it look like this is easy to solve for x or difficult to solve for x? The equation is 148.6. Maybe this is easy to solve for x, right? Is it? I think this would be not difficult to solve for x if you bought the calculator. What kind of calculator do you guys have? Did anyone get that Casio? You could just solve it easily with the Casio. But you have to do a little bit of work because for the Casio you have to get it in a certain form. For the Casio you'd have to get it in the ax cubed plus bx squared plus cx plus d equals 0 form. And then In the Casio, you would just plug in A, B, C, and D, and then it'll solve it for you, right? But you can't always rely on your calculator, because the Casio, you know the maximum order you can solve in a Casio? Third order. If I made it fourth order, you couldn't solve it, you know, because this is the limit of what you can solve with the Casio, because if it were AX to the fourth, forget it. You're not going to be able to do it. And so, if you don't have the Casio, how would you do this? Do you know how to solve this kind of equation much? How long would it take you to solve for X? 10 minutes maybe? 1 hour? Well, I've given it, and lots of people haven't been able to solve this problem. Lots. Given this type of problem, and let's say the majority of the class failed in solving for X. Why? Well, you know, even though it's simple algebra, it's not simple. You know, it's not simple algebra. This is tough. This is not so easy to solve. Unless, did somebody solve it already? Oh, Kelly. What did you get for your X? What is it? Around 0.1? Well, you just go ahead and give me 0.1.
Wouldn't the X's cancel out?
Hmm?
I just plugged in random numbers.
Okay, you plug in random numbers.
Wouldn't the X's cancel out? Like,
The X's won't cancel out,
But then
unfortunately.
would be multiplied and there will be x cubed on the top and the x cubed on the bottom.
But the coefficients are different. You can't cancel them out because this is x cubed plus this plus that. And so you can't just cancel out an x cubed. You can't do this.
Is that a 0.389.2 or?
Yeah, 3
Or minus 2?
minus 2x.
It's minus 2. No, that makes sense.
Okay, you can't cancel. This is minus. Those come from over here. All right, what Kelly did is correct. What Kelly did is, most people aren't going to have a Casio. And if I did a fourth order or fifth order, you can't use that calculator anyway. So we have to use what she did. What do you call your method there, Kelly? We did it for solving the van der Waals equation for volume. Do you remember that? And it was the method is in Appendix A, and it's called it has a fancy name. It's called you remember? Paul, you remember? We did it once, and you might not have had to do this in Chem 1A. I made my Chem, I assigned a problem where they had to do it in 1A because it was too hard. And so if you need, second order is easy. Second order we could use the quadratic formula, this is in Appendix A1. If you have the calculator, then it saves you a heck of a lot of time. You don't have to do this. This is quadratic, but if you need a review of how to solve the quadratic, this is it. In Appendix A1. Also in Appendix A1 is graphing, but at the end of it, Appendix A1 is something that's very useful for us in Chem 1B. In fact, we're going to use this a lot in Chem 1B. And what is it called? Shoot. It's called, where is it? I passed it. Shoot. Let me just go 1 minute over time here. Oh, wow, they changed it, I'm sorry. In the 11th edition, they got rid of the section. Now it's just incorporated in the quadratic section. But it's called the method of successive approximations. You'll find it on page A6. Here's a fifth order. You aren't going to solve a fifth order with your calculator, even if you got the Casio FX115. The max you can solve is third order. And so how do you solve a fifth order? algebraic expression like this for x, you would use the method of successive approximations. A lot of people learn the method of successive approximations in elementary school, but they don't call it the method of successive approximations. They call it the guess and check method. And so we're going to use the guess and check method to do this. And that is, we're going to guess. So Kelly guessed the value, and she got something around 0.1. We need more precision than this. And so we keep guessing until we get a higher precision. So we'll finish this next time.